For some time now, private companies along with NASA have been developing new spacecraft to take astronauts to the International Space Station. The space workers are installing new docking modules.
One of the big steps, of course, was the removal of a large thermal cover by Rubens and Williams to expose the actual docking port to which the SpaceX Crew Dragon and
The station currently has 8 docking ports. In addition to the passenger craft, there is another kind of vessel that docks with the space station: supply vehicles.
We have a lot of unmanned resupply vehicles that get sent up to the space station. We have Japanese resupply vehicles, we have Russian, we have American.
Every 3 months, these vehicles supply the space station, delivering water, a few fresh products, clothes, tools, and experiments. Once emptied, these supply vehicles have another key function. They are used as the space station's trash can.
Space station is a closed system. Everything that you bring up at some time needs to come down. So if you bring up clothing, for example, for the crew, we don't have a washing machine, so the crew has to wear the same pants. You get 2 pants for 6 months. You have to wear the same T-shirt for a week or for 2 weeks. And then when it's finally dirty and it's trashed, all this trash is accumulated in the cargo vehicles.
Come join me in the Progress vehicle, which is loaded and ready to leave. It's filled with bags of rubbish. I need to crouch right down because there's not much room. I'll try and show you. Everything is arranged symmetrically to balance out the vessel. Heavy things go opposite heavy things. You can see here, for example, there are purification columns, buckets that we've used, and even our dirty laundry, and little packages with our trash.
The vessels filled with trash are then unmoored. They burn and disintegrate when they enter the Earth's atmosphere. But some of the supply vessels fulfill a last function that directly involves the ISS. They are used as motors because the station is unable to maintain the right orbit on its own.
The idea is the ISS is about 220 to 250 miles above the surface of Earth. So you might think, well, so there's no air, so why would you ever need to speed up? It should just forever be in orbit. Well, where the ISS is, there's actually a very thin amount of atmosphere there. It's borderline negligible, but it is still there. So we have basically this giant football field. I mean, a vehicle the size of a football field flying through space. It's getting a lot of air. There's a lot of surface area that's getting hit by the small amount of air that's in the atmosphere. So that does slow the ISS down.
And so the ISS altitude is decaying by about 2 kilometers per month. And if it were to have no reboosts, then eventually the space station would re-enter Earth's atmosphere.
Every 6 months, a supply vessel is used to readjust the orbit of the ISS. The vessel starts its motors and emits bursts of power to get the station moving to the right altitude. The thrust can be felt inside the station itself.
Now, the way I'm going to demonstrate the acceleration that comes during the reboost is by using this camera. 800 millimeter lens, so it's pretty massive actually, and there's no accelerations, virtually no accelerations on us, and you can see I'm floating this camera right here, and it's not going anywhere. And I'm holding it, I'm actually feeling the acceleration. I'm going to let go again, and here it goes, it's going to take off. I'll try not to let it hit you.
But it's not only the height of the orbit that needs to be regulated. They also have to keep the space station angled the right way.
So the space station maintains what we call LVLH, local vertical, local horizon. And that means that the space station flies around the Earth, always Earth-facing.
The station's steering system is based on 4 gyroscopes. Without them, traveling at 28,000 kilometers an hour, the ISS would turn endlessly on itself, and life inside would be simply impossible.
In zero gravity, if you knock it, it's going to tumble, it's going to move around like any object up here does. However, if I get this spinning, so once the gyroscope is spinning, you can just see how stable it becomes. And however I knock it, it's not going to change its plane. It's going to remain in the same plane.
The gyroscopes turn like a spinning top or bicycle wheel to ensure stability. But the rotation axis of the gyroscopes is also controlled, allowing the station to tilt to follow the curve of the Earth.
By maintaining this LVLH, it means that we have a great Earth observation platform. That's why our cupola window is always looking at planet Earth.
Play that.
When they aren't carrying out scientific experiments, the astronauts are busy maintaining the station.
We do have one of the most important pieces of equipment on the International Space Station hidden up here. This is the vacuum cleaner.
Although a filter system ensures the elimination of particles and certain microbes, regular cleaning in this confined environment prevents bacteria from growing. It also allows them to find parts they thought were lost forever. There is always work being carried out on the International Space Station. The daily lives of astronauts include plenty of time taken up with repairs and improvement work. But despite all their precautions, there are sometimes breakdowns and even major damage. That's what American astronaut Tracy Dyson discovered one evening in July 2010, just before going to bed.
Everybody else had gone to bed, and I was doing my routine checks of the space station on the US segment. I was turning off the treadmill when all of a sudden red and yellow bells and whistles start going off, and it was way more than just our treadmill having a problem. And then it became pretty clear that there was a problem with the thermal control system.
The thermal control system is vital for the astronaut's survival because outside the station, the temperature varies between minus 150 degrees in the shade and plus 120 degrees facing the sun. On board the space station, the electrical apparatus, and in particular the computers, generate a large amount of heat. To get rid of this heat, the ISS has a cooling system. Cold fluids flow around the entire station. There are water-cooled circuits on the American segment. The central beam and the solar panels are cooled using ammonia, and the Russian segment uses a combination of chemicals.
We knew that the most critical thing that could happen at that point was if we lost our other pump module. If we did, then we would have to start considering whether to go home.
On the ground, as in the station, the crew realized that the situation was critical. To replace the defective ammonia pump, they would have to go outside the station and repair it from the exterior. More dangerous than any other activity, spacewalks leave no room for improvisation and require lengthy preparations.
All the days leading up to it are filled with activities that have pretty severe consequences if you don't do them right.
If a cosmonaut tells you they aren't afraid on a spacewalk, or that they did a flight to the ISS and were calm and had no fears, then they're lying.
There are 2 depressurization airlocks for spacewalks, one on the Russian part and the other on the American section.
Inside the space station, it's got the volume of, say, a 5,000 square foot house. So it's a huge volume, but that's a fraction compared to the outside structure.
Humans are incapable of surviving in the space vacuum. There is no oxygen, the body is exposed to extreme temperatures, to micrometeorites and cosmic rays. Carry out the repairs, the astronauts therefore have to wear some extremely high-tech gear.
The spacesuit is a phenomenal piece of technology and engineering. It's a mini space station. It has to keep you alive.
The astronaut survival has a price because these spacesuits cost $15 million apiece. They are composed of a bubble helmet covered in filters to protect their eyes from the sun's rays, which could blind them instantaneously. Powerful lamps are there to illuminate in the dark, and a camera sends images to the ground. A small tube right by the mouth delivers water to the astronaut during their walk. Earpieces and microphones allow them to communicate with ground control and the rest of the team on the ISS. On the front of the suit, dials control the oxygen feed and temperature. Beneath the spacesuit, the astronaut wears a piece of clothing crisscrossed with plastic tubes through which cold water flows to regulate the temperature. A backpack contains reserves of oxygen and water, along with batteries providing total autonomy for up to 8 hours. Because of the absence of gravity, the astronaut cannot feel the weight of these 130 kilograms of equipment. But being able to move around with such a suit on requires exceptional physical capacities.
90% of what you're doing outside, you're doing with your arms and hands. And because it's a pressure suit, even moving your fingers in the gloves takes effort to open your hands, takes effort to close your hands because of the pressure and the stiffness of the gloves.
Such a task requires constant focus, and here, more than anywhere, there is no room for error.
It's one of the hardest, if not the hardest things that we do in space. It's not just physically difficult, it's also mentally difficult, because you are not only fighting against the pressure of the suit with every motion that you make, but you are concentrating the entire time. And the spacewalk itself is anywhere between 6.5 to sometimes 8 hours long, without a break. You're inside this spacesuit.
Assembling and maintaining the station required more than 1,000 hours of spacewalks. During these sorties, the astronauts carried out numerous essential tasks for the station. Without these spacewalks, the ISS wouldn't exist. At 400 kilometers above the Earth and outside the station, Tracy Dyson and Doug Wheelock hurried to remove the defective pump and replace it with one of the 4 replacement pumps on board the ISS.
Bigger than a refrigerator. It's very, very large box, very massive. And it, thankfully, we had the use of the robotic arm. Doug Wheelock was on the robotic arm, hanging on to it, and then I translated and met him in the spots where we were taking it from and putting it in and helping to guide it.
4 spacewalks of 29 hours in total were necessary for these extreme plumbers to successfully repair the heating system.
The ground teams regained the cooling, and we powered up the space station, and we saved the space station. How about that?